This is part 3 in our series of lectures on section 3.1 on Cartesian products and relations. And in this lecture we talk about the composition of relations. Let's begin by looking at the idea of composition intuitively before we give the formal definition. Suppose R is this relation and S is this relation. How should we define R composed with S? Well, we start with this entry here, this 1, 1. So that tells us that R relates 1 to 1. Now we follow this 1 here and we see that S relates that 1 to 6. And so we want 1, 6 to be an element of R composed with S. Let's look at this 1, 2. R relates this 1 to 2. Then we follow that 2 here and we see S relates 2 to 1, and therefore the composition should relate 1 to 1. R relates 2 to 5, and 5 isn't related to anything by S, so we don't do anything with that entry. R relates 3 to 4, and we find 4 here. S relates 4 to 0, and therefore we should view R composed with S as relating 3 to 0. So that tells us what we should write down for R composed with S. So there you have it. That's what the composition should be. Now look again at this 1, 6. We got 1, 6 because R related 1 to 1, and this 1 was related to 6 by S. So we have this linking term, this middle term 1, 1 is common to both. Similarly, this 1, 1 came from looking at 1, 2 and 2, 1. So this 2 is the linking piece here. And 3, 0, we got 3, 0 in the composition because we had 3, 4 and 4, 0. So again, we have this linking term, this 4. Okay, so we can use that idea to write down the formal definition of the composition as follows. If A, B, and C are any 3 sets, and R is a relation from A to B, and S is a relation from B to C, then we can always form the composition of R with S. We denote it in this way. This is the composition of R with S. And it's a relation from A to C given by the following. It's the set of all ordered pairs A, C in A cross C with the property that there exists this linking element of B. It has the property that AB is in R and BC is in S. Okay, so that's a very formal way of doing what we intuitively did up here with this particular example. But you'll find that when you're actually writing proofs involving compositions, this working definition becomes essential, and this intuitive way of looking at it up here won't be good enough in order to write formal proofs. So just to recap, an element AC lies in the composition R composed with S, provided there exists a B in B with the property that AB lies in R and BC lies in S. Let's look at one more example. This is purely computational. We're not proving anything in this particular lecture. We let R be this relation here. We let S be this relation here. So R is a relation from 1 to 3 into UVW, and S is a relation from UVWXY to the set 1, 2, 3, 4. So does it make sense for us to talk about the composition R composed with S? Well, we said that R is supposed to be a relation from A to B, and S is supposed to be a relation from B to C, but here these two things don't match. But that's okay. When we said that R was a relation from here to here, we can always enlarge this set, because after all, a relation is just simply a subset of a Cartesian product. And so I can enlarge either this set or this set. I can make it anything bigger than that at all and still view R as being a relation from the resulting set, the resulting enlarged set to the resulting enlarged set. So I can view R as being a relation from here to here rather than just simply this. Okay, so therefore this is a relation, and it's a relation from this set to this set. Now let's see if we can calculate what it is. So let's begin with R. R starts with a 1. 1 is R related to U, and S relates U to 1. So we'll have 1, 1 in the composition. 1, R relates 1 to V, and V is related by S to either 2 or to 3. So we'll have both 1, 2 and 1, 3 in the composition. R relates 2 to W, and W is related by S to 3, so we'll have 2, 3. R relates 3 to W, and again S relates W to 3, so we'll have 3, 3. So those should be all of the elements of the composition are composed with S. Now what if we go in the other direction? What if we do S composed with R? So S is a relation from this set to this set, and R is a relation from this set to this set. So once again, remember, we can always enlarge either this set or this set at our convenience. So we can view S as a relation from here to here. We can also view R as a relation from here to here. And therefore, S composed with R will be a relation from here to here. Now let's see if we can calculate it. S relates U to 1, and R relates 1 to U and also 1 to V. So we'll have UU and UV in the composition. S relates V to 2, and 2 is R related to W, so it will be VW. S relates V to 3, and R relates 3 to W, so we'll have VW. S relates W to 3, and R relates 3 to W, so we'll have WW. S relates X to 4, but R doesn't relate 4 to anything, so that doesn't go anywhere. S relates Y to 1, and 1 is related by R to both U and V, so we'll have both YU and YV. And finally, S relates Y to 4, but R doesn't relate 4 to anything, and so that doesn't go anywhere. So this is what we get for the composition of S composed with R. Notice, by the way, that the domain of S composed with R is strictly contained in the domain of S. The domain of S composed with R is U, V, W, Y, whereas the domain of S is U, V, W, X, Y. It's got that X in it, which S composed with R doesn't have. So relations aren't exactly like functions in that way. If you have a relation on a set A cross B, the actual domain can be a proper subset of A. It doesn't have to be all of A.